last day of the workshop with Marius Junge, speaking on complexity and dynamics from finite to infinite dimension.
Yeah, and I totally forgot my cover page. I don't know what happened. Probably went into the copy. So this is joint work with Li Gao, who is here. Nick Clara Corrente. I will probably not write all the names. Hao Jian Li. And more recently, Chu Wu, who will go to Waterloo, Roy Riza, and Yidong Sheng. And yeah, he just graduated yesterday, literally during the conference. So, and unfortunately, I cannot keep him academics. If somebody else has an idea, can you vote him in the paper? Like, then he's welcome. So, my plan is to actually do exactly what the title says, where the dynamics will be a little bit suppressed. I will come to it a little bit later. I will start some complexity. I will explain how we found a nice definition of complexity to generalize and see first how that works in finite dimension. And then somehow this gives a roadmap to go to infinite dimension. And we will follow that roadmap, because then we can easier understand, where the problems are and where the transition happens. So for seeing that one, unfortunately, needs a roadmap. So we will first support all these Wasserstein dependent complexities. Then I will tackle a little bit of the technical problem, which occurs. The definition is a 5 minutes job, so there's nothing to say. And then we will pass to infinite dimension. Now, I have to say that the black holes I put in the abstract, that is more questions than answers. So this is just at the very end. It's maybe I shouldn't have done that, but anyway, it looked fancy, so I was tempted. Yeah, sometimes we are tempted because we think things are cool we don't understand. That's what's happening there. Okay, so let's talk about Wasserstein complexity. So I visited Harvard last year, and then Jeffy asked me this million questions in his office, and I had no idea why. And then I saw the paper in the archive, and then I understood why. And they came up with a brilliant definition. I have to say, the brilliance is just to write down these axioms. The work was done, honestly, by Giacomo di Parma. He did kind of the hard work of proving some of the properties, but they formulated a notion of complexity for channels, which has the additional property of being convex. Now, in quantum information, working with convex functionals, right, or measures is always an advantage. But if it's not a priori convex, you pay a huge price making it convex. I think we have seen this in one or the other instance. All of us has somehow confronted with that problem. So here, convexity is built in as an axiom. So the first axiom is the most doubtable. The complexity of the identity is 0. Does somebody have seen small children? Standing still is one of the hardest exercises, right? Right? So doing nothing it's not easy, right? So that is an axiom. You get tenure. That's your answer, but this is certainly an axiom which can be debated, right? I mean, there's no question, but I mean, I'm following their approach. It should be sub-additive or sub-multiplicative, right? So if you compose channels, complexity goes up. That corresponds to, often complexity is defined of complexity of using unitary gates. And then if you do one after the other, the complexity should be not more than if you do one step and then the other step. So this is where sub-additivities come from. We just mentioned convexity is kind of a convenience assumption, which you want to have in order to prove good estimates. This here, tensor additivity is certainly nice to have, right? So this somehow says that if I have some action on Alice's system and some action on Bob's system, I combine them and I don't get more. We will also see how that works. And then there's the normalization condition that, it shouldn't grow more than the number of qubits, right? So that's a reasonable assumption because many of our calculations, if they're, beyond the polynomial in the qubits, they're kind of hard to imagine or hard to realize. Anyway, that's a preferable estimate. And so then we gave an example. I will not mention the example now because it's a special case of an example which comes up later. So in the names of efficiency, I will just say that they find a good example from the Wasserstein 1 metric.
De Palma's work?
Yeah,
Giacomo De Palma.
check
The spelling.
I'm not good with that, but we know whom we're talking about, right?
Yeah, I know.
And the statement about is correct. Okay, so so here is an example how you create such a complexity out of the blue. So you give yourself a set of operators. Now here B of H could be finite or infinite dimensional. I don't really care, but if you want to make it concrete, take a set of operators in a finite dimensional Hilbert space, and then define a norm on operators. F here is kind of an element in A, so some kind of non-commutative function. So an observable, if you wish, and we just calculate the supremum over the commutators. Yeah, so that's if you commute with all of them, that's a free resource in a way. And if you don't, then you have to pay. That's what you have to pay. We can also do this for matrix valued function by just doing one tensor S. And it's in this sense, this space becomes an operator space. I'm not going to talk about operator spaces. I just have to mention it's a natural one, which has been considered before. And then we can talk about the norm from this space A0, which is the space of all of A divided by the null set, right? So I'm cheating here a little bit. I mean, how this identity acts, one has to be a little bit careful. I will explain that later on, but it actually is kind of the right thing to do. And so we calculate the norm either of phi is a map from A star to A star. So phi is a channel, right? The pre-dual of a C star algebra is a set of states. So a channel goes from states to states. That's kind of the easy philosophy. If you have a channel, trace preserving, completely positive, or positivity preserving, and the dual is unital, then you can define the complete or the non-complete norm by phi star minus identity from this Lipschitz space to the algebra back and here back. So as I said, I will discuss this little trick with the identity, but it's somehow right to think of this as the algebra modulo. It's a new norm, it's a norm, and it's only a norm if you mod out the zero functions, right? So that this works as a condition. And yeah, so this is my definition. And then you check some elementary properties. Now, okay, if phi is the identity, then phi star is the identity. Identity minus identity is 0. So this takes care of the children. This here is a very easy exercise. It's really, norms and plus and minuses. So this additivity, and here, if of course, if the norm is 1, then this is the additivity, and channels have the property that phi star is norm 1, right? So since they're trace preserving, they're also contractions. So this is the additivity property, but if you want to do it for arbitrary maps, you would have to invoke the norm. It's kind of a Lipschitz type condition.
CSI or one should be CS5? No.
The norm of a map is the norm of a dual.
No, it's type 1.
Oh, this is a phi and a psi. This is a psi and no, this is a phi and a psi, and this is a phi and a psi. Yeah, you are right. Yeah, self-correcting. Thank you. Right, so this is wrong. I mean, you have to switch them, right? Then there's a very easy, simple estimate. So if I have a conditional expectation, some kind of projection on the, think for a moment that the set of S is adjoint under taking stars, right? Then you can look at all the elements which satisfies Fs equals 0. And that is a star algebra itself. The commutator of a set is an algebra, and at least in the finite dimensional setting, it's super clear that then there's a projection onto the subalgebra of invariant elements. These are the fixed points. In many cases, you want this to be just the identity, but if you give yourself an arbitrary resource, you just don't know. Yeah. So if we take this conditional expectation from the algebra to this fixed point algebra, which I call E fix, then we can do a very simple norm estimate, and we see that the worst case is the complexity of this particular channel. And then we have identity minus phi or identity minus phi CB norm, depending on which of the two things I'm doing. And for a good thing, we know that for a map from A star to A star, the CB norm is less than 1. Identity minus phi is less than 2. So the worst thing we can have in order to get these logarithmic estimates is we just have to talk about one object and estimate that one, right? Because then we have it up to a constant 2. Okay, if you, I'm liberal with a constant times log n. So I'm allowing that. So in order to get the last axiom done, we just have to talk about this quantity and estimate it from above. And then we satisfy all the axioms we want, right? Good. And here, this is a super nice exercise, essentially also following an argument by Giacomo. If you adopt that and read what he did, you just translate it and you get this complete additivity. But for this, you have to go complete. You have to tensor with an extra environment. I mean, it's a standard trick somehow. You have to, we've seen this also many cases, right? You add some arbitrary environment and something becomes additive. Here, the same idea here, and it's pretty straightforward if you understand this first. Good. So yeah, so this means for every set S, say self-adjoint, we have seen that most of the axioms here. So if we go to the CB version, we have this version, right? This one we have to discuss. That's the number 2, right, in my plan. And these properties are kind of all for free. And so then we have many examples, but they are resource dependent. They depend on the choice of S. So imagine you have a set of gates, which you can implement easily. And that does happen, even in experiment. They cannot implement all gates. Nobody claims they can approximate all gates, but they cannot implement all them. So if this is your basic set of gates, you just call that resource S. And then we can work with that resource and see what you get. Well, and you can measure how expensive is a channel, because, you know, complexity in this case is some kind of cost, right? How expensive is it to implement such a channel? But you're allowing for convex combination. So this means you can combine unitary channels plus some measurements and then repeat. That's convexity, allows you to do that, right? So you have more channels to add. And so the whole problem is to find lower bounds for this complexity, right? Because, you know, upper bounds, you just write down a convex combination of unitaries and then it's there. But the lower bound is, of course, to show that, you know, you have a resource which is not for free. That's a whole challenge. But we will first address this question. Good. Let's go for that.
So
And-
one
yeah.
question. Why is the tensor additive so natural? Because if I think that these could be maps that may induce interactions, for instance, right? Then I don't see why necessarily would have to be that the complexity of the tensor product is just the sum.
So the answer is, it was proposed in the axioms and they considered it natural. Okay, so I mean, that's not the satisfying answer. But if you look what I did, I introduced 2 of these objects. Because for this one, I cannot prove additivity. So it's not natural. I did a trick to make it happen. But I did a standard trick to make this a mathematical trick, right? So I changed my definition in a way that it becomes completely additive. So no, and if you just have one resource, I wouldn't say it's natural. Yeah, but you know, but if you have access to environment and then define it, if you have enough access to environment and allow for channels to act on an additional environment, then you have to also measure the complexity of phi tensor identity where identity doesn't act, right? Then if you have to do that anyway, then you're in the second category automatically, right? If not, you don't really know what to say. So it's natural from a math point of view, essentially because we know how to do it. But if you have a fixed resource for a small number of qubits, I don't think it's natural. But that's, you know, then you're criticizing Mr. Jaffe et al. And not me, right?
So sorry, so S
Yes.
is a set of resources, so
Yeah.
it's a set of gates that you.
Gates,
Uh,
Selfadjoint operator. I will give you many examples which justify that, but yeah, we will see some examples which illustrate possible choices. And in fact, my whole talk here is your question. Yeah.
Excuse me.
You somehow took my point away, right? I mean, what is S? How should you choose S? Does it have, what kind of conditions should we look for? Is exactly the question, but without making some restrictions like, okay, I mean, if you say we have finite energy, I mean, you cannot work with everything because then it's too wild. So you have to do some constriction, some extra structure. And my suggestion is, well, take that and there are motivations for this, right?
And classical Wasserstein, I mean, this appearance of the commutators is a bit strange.
It is.
So the Wasserstein distance would be written in terms of just a set of Lipschitz functions.
Yeah, but
It's
what is
like
it?
that. But you don't have that. I know, but it's not.
Can we,
So
I mean, I love your question, but that part we have to postpone 5 minutes later, okay? And then we have that again, because it's a good question, okay? It's just that the answer is 2 pages later. No, it's here. Okay, so I copied part of this definition because I read Kahn's non-uniform geometry, and he wants to define the most simple version of geometry he can think of, right? I mean, and Mr. Kahn was very successful with that. But so what is the geometry, the beginning of a non-uniform geometry for Mr. Kahn? He starts with a C-star algebra, or actually not a C-star algebra, a star algebra, because, you know, he thinks of algebras of smooth functions, Lipschitz functions. And then he has one Selfadjoint operator, and he requires that these smooth functions, the commutator with D of A is finite. And that's the definition of a spectral triple. Yeah, and then he gives an example. Take the Dirac operator of a spin manifold. You don't have to know what the Dirac operator of a spin manifold is. Maybe you want to know, but you don't have to. It's here, the torus is an example of a spin manifold, right? And the Dirac operator is DDT. Everything else is a little bit more complicated, and there's an abstraction for arbitrary manifolds to be spin, but that's really more for the other topics. They know how to do this. But the main observation is, if you define the norm FD as the norm of the commutator, it turns out to be exactly the Lipschitz norm, right? So this is just the Lipschitz norm. So we are asking, Wasserstein distance is somehow related to the dual of the Lipschitz norm, and that's the concept we are actually following on the nose, right? Just that we allow for more than one Dirac operator, which you could formally do by writing them in a long diagonal and then make your algebra larger. It's just that for me, keeping track of these generating resources from the quantum, you know, if I have a concrete gate set, I don't want to write, you know, I can write a list, or I can just, yeah, it's better. So, and here's an example where this resource generator thing works out very well. So we can take a discrete group. I mean, a finite group. Sorry, I should have written finite group. That's certainly good there. What is my algebra? My algebra is L infinity of G, functions on the group. I can take a generating set of the group. So a generating set is a group where if you write products, you get everything. That's your resource. And then you calculate the worst constant situation. And it's exactly the average over the distance from the group element to identity, and the distance is the smallest number of generators you need to reach that element, right? So this upper estimate here is really some version of average diameter, you know? So this upper estimate is the average diameter, and that is an example of how to calculate these diameters, right? They're average diameters, but I prefer to think them of diameters. Here, this extra mean zero condition doesn't spoil you. You can always arrange for that to happen. So if we take a resource from geometry, then the dual object is exactly the distance between points, and the distance between points, the distance between states, is dual to the Lipschitz norm on the functions. That's what I want you to remember. And Lipschitz norm is defined with respect to the resources we like to work with. Well, and that's it. Yeah. So this is a motivation for our example. That answers your Lipschitz question, right? It's there. It's just another way of talking about Lipschitz. Okay. Yes, and that's why he works with DDT and not the Laplacian. Because if not, it wouldn't work. Okay, good. Other kind of examples which are natural. Take a Lie group. Where is Mr. Yeah, we are back in your situation. We take a subset of the Lie algebra, a Hermander system. So generators create the Lie algebra. We take the group is SUN, and then we are looking for the set of S are kind of these elements in the Lie algebra. And yeah, then you can actually work in the algebra itself, right? So if you have a Lie group and you allow certain directions, but you're forbidding others, you can often still reach every point. This is super interesting in the Heisenberg algebra. Heisenberg algebra has X and Y and Z is missing, or it goes into the center and you're not allowed to talk of it. But still by zigzagging, you can reach every point. That zigzagging argument, which I tried to do on a picture, but you know, in real nature is much better, is goes back to Chow, right? I mean, that is the beginning of sub-Riemannian geometry. It's a field. They worked on this forever. There's a big difference between sub-Laplacians and Laplacians. The number of people who know Laplacians versus the number who know those sub-Laplacians is probably a ratio of 1 to 1,000 or something like this. I don't know the ratio, of course, but I mean, sub-Riemannian geometry is much more special, but there are some people who like it, like Gromov, right? So not so bad. Anyway, so you have to think of restricting resources. And in fact, before I started to write this stuff down, I saw a talk in one of our joint IQUIS seminars, which are trying to connect experimentalists and theory people. And the person really just wanted to see how, if you modify your XY gates by some slight rotations, can you create the same resources after 4 steps? And then she showed these pictures of, you know, how if you move inside a little away from your XY gates, how you can still get everything. So that was, that's something she studied explicitly, and that's exactly the question. You know, can you do in 4 steps? Where can you go if you remove your XY to an X theta Y theta slightly rotated version? So it's rather, it appeared natural there. So it does occur. Good. And now we will have to talk a little bit how to get rid of the logarithmic estimate. That's kind of the mathematical work I have to do. And that's related to Lie's talk. So here we do actually have dynamics, because I'm working with a Lindbladian without H, right? So this is just noise. So for me, it's just a noise, and the noise determines the dynamics for this problem. And then in abstract, in semi-group theory, this is the dissipative form, very well known. You can define another Lipschitz norm, which is the maximum of those. That's another Lipschitz norm. We can look at the limit if it exists, but in our case, mostly it will exist. And this kind of conditional expectation onto some fixed point algebra. And the definition of CLSI is that you have this entropy decay behavior, even if you couple the system. So that's the definition. The best constant, the best alpha, which works for all couplings, is the CLSI constant. And as I mentioned before, we introduced the complete version to make it additive, or, you know, not additive, but the CLSI constant of L tensor 1 plus 1 tensor L prime is bigger, right? So this control of the constant was essentially just, again, a wishful thinking, and then we just declared that's it. We have to work with this one. Yes.
Yeah, second term in the definition of gamma, is that what you want, or is that a typo?
No, I want that because in principle I can talk about the Lipschitz norm of non-Selfadjoint functions. Of course, if you only have Selfadjoint observables, it's not. But if you think of matrix valued functions, you're adding a transpose there somehow, right? Not really, but so no, this is meant to be. Yeah. Good. So this is our definition of CLSI, and you know, over the years, And with the help of many people, there are now some known estimates. And here is the Wasserstein, dual Wasserstein distance. So for rho is a density on element in A star, I wrote it with a trace, but I could have written it down as yeah, so this is that's a trace-free definition, if you wish, right? I mean, if your density is given by the trace, then you're happy. But if you want to do this in infinite dimension, no problem. Just phi of f minus, you have to remove this mean zero part. That's how we work with it, right? So, and that's the dual norm. And if this were to be a manifold, this would somehow recognize the distance between points. We have seen other works which want to try to understand, on the state space, how can we do geodesics on date space? That has been studied in different contexts, but this is one. And so we know that CLSI implies that this here is less than a constant square root of the relative entropy. Yeah, that's a paper of ours. And if you have a matrix algebra here and the fixed point algebra, always the worst case relative entropy is always less than, well, log n, right? Because the identity is there, so you never get worse than log n. So this means that we have a constant, we can estimate the dual by square root of log n, which is not log n. Well, so something has to still be adjusted. We are looking for log n. Where's the log n coming from? But this gives us a good tool to have these kind of estimates of diameters. They come from these anthropic inequalities, right?
So sorry, would that be kind of related to Pinsker's?
Yeah, in a way, yes. It's kind of an improved. It's kind of, yeah, no, it's not exactly, but it's similar to Pinsker, but with a different norm than the one distance, right? So we are using a different norm. Now, this here in this form can happen in infinite dimension. Pinsker is a little bit complicated in infinite dimension. Yeah. Okay, so here's the case which is a little bit cleaner. Namely, if we take a self-adjoint Lapladian. Self-adjoint Lapladian are very tempting if you come from commutative theory, because self-adjoint semi-groups are much nicer than other ones. They're reversible and whatever. For those, we can do a lot, and I will tell you a little bit what we can do if it's not the case, but let's have, a nice Friday morning and relax a little bit. So in the self-adjoint case, we can simply work with a Lapladian, which is given by double commutators, which corresponds to two derivatives geometrically. I mean, we can all see that on the nose. And then, of course, my resource are just these AJs. That's the natural choice for the resource. And often we just want to have a finite number. I mean, we could work with infinitely many, but then do we have even functions which belong to the domain? Here we do. Okay. Anyway, so this is our new norm. And in this concrete case, this Lipschitz norm from the Lapladian is just the sum of squares of the commutators. And in particular, if there are only m, it's less than square root of m times the Lipschitz norm for s, right? So that's a very simple estimate, and that's it, okay? Because now we can have the following result. If we have Wasserstein 1 estimate, right, this generalized Pinsker inequality, then we get a constant only depending on the generator, square root of m for the number of terms, and square root of m for the dimension of the qubits, right? And if m is equal to n, you get n. And what is a good example? Take as a resource xj's and yj's, right? So x is the Pauli matrices. I put them in the j's register, right? So these are the natural xj's and yj's in m2 to the n, right? 2 to the n. And of course, there are 2n many. So the number here is 2n, and then it is known that this this corresponding Lipschitz has CLSI independent of the dimensions. It's actually this additivity property. You just have to prove it for the two-dimensional case, and then you tensor. And the two-dimensional case is actually one, I think. That's very simple. Nick knows that two-dimensional case extremely well for X and Y. CLSI for the generator given by X and Y in 2x2 matrices. Yeah, we talked about this like for ages, over and over again. Yeah. So this constant here is actually one, and we end up. And then if you look at the definition which they got from Giacomo, you realize that we're talking about an equivalent definition, right? I mean, that is their definition of Wasserstein convexity. Yeah. So this is just one example, but this works out together well. Okay, for compact groups, I'm just repeating some of the work which we did with Li Gao and Hao-Jan Li and Nick. So what we do is we start with the compact group and the Hermander system, because we already have a good system in this compact group. And we have a ton of harmonic analysis giving us these order estimates, which we use for our theorem. So if we follow that theory, then we can look at representations of a compact group. And there are many finite dimensional ones, infinite dimensional, it doesn't really matter. And what we do is we take these directions and we differentiate in the direction of the Hermander system. If you differentiate, that's a one parameter groups, then they're given by some operators in the corresponding Hilbert space. You know? So they're one parameter groups of unitaries, they have a generator. We call that the generator AX pi. We define a Lindbladian double commutator, you know, double derivative goes to double commutator, how it should be. And for those Lindbladian, we have an estimate of the CLSI constant, bounded above by the spectral gap that was known, and bounded below by the spectral gap plus a constant here. So if the spectral gap is less than 1, we confirm what everybody believed to be almost all the time true, but it's actually not always true, that the CLSI constant should be equivalent to the spectral gap. You know? So that's a confirmation, but we need this extra assumption. This constant here is not trivial, right? And that constant is simply saying that the heat kernel on that Hermander system at time equals 1 is bounded. Yeah, that's it. That's what we need. Anyway, and this gives you actually a uniform point of the diameter if you take these guys here as resources. So the diameter does not grow for a fixed representation. It's uniformly bounded for all representations. Okay, sounds a little bit too good to be true. Well, here, if you go to tensor products, because of the complete additivity, if you take tensor products of a representation and take the new resource, which says in every component, I'm allowing the same set S, right? Like the XJs, they're in SU2, they're copied in all registers. If you do the same procedure, allow them everywhere, then the resource goes up, and it's exactly additive in the number of tensors, right? So the maximal diameter is n times the diameter of the original system. And that's kind of, so the analog of Wasserstein distance is in the presence of group representations is just take tensor products of a given representation. And then you have a resource which exactly mimics the first axioms, right? So that's how we create examples. And just to mention this beautiful result for SUN, so this was for 2, but for every n, you can find 2 generic with log n many generators. So this should be an SUN, right? So that's exactly what we said. So in every dimension, you only need 2 resources, and that's enough. Well, a bit surprising. Of course, the constants can screw up in higher dimension. The constants screw up, but the number of directions, the number of resources, we expect them to be just 2. But that's exactly where things get tricky. So now I want to give you an example when we try to move from finite dimension to infinite dimension, how we do that. So when am I supposed to stop?
Quarter past, 20 past.
20 past. Yeah, so you know, a very natural resource is to just look at photon emission operators. And If you do that, then you look at these, this is the definition you're summing up. It's kind of the Lie. Well, let's just look at these operators. So we are taking Lindbardians, where we take these two terms, and we are just essentially looking at the representation of the X and the Y gate in the tensor product 2x2 matrices. And that is an actual derivative. It's exactly one of these AXs. And then we can consider Lindbladians with few terms. In the Selfadjoint case, we can just use X and Y, but in the non-Selfadjoint case, if you want to fix some kind of thermal state given by the Z direction, we have to follow a Carlin-Mars procedure and go for the image of 0, 1, 1 and 1, 0, 0, right? So we are splitting up our X operator into an upper diagonal and the lower diagonal part. And that gives me a Lindbladian. And if you tweak it a little bit like this is a new Lindbladian, which fixes the thermal state. Yeah, so L beta n star of rho beta is 0. Yeah? So these are natural Lindbladians. And we can ask, okay, what are the resources? Now we have two resources. What are the properties we can work, right? I mean, we're asking for finite diameter, CLSI constant. And for beta equals 0, everything is known thanks to the work on compact groups. But for positive bit in temperature, we tried for, I mean, I tried, Guidon probably knew better, but I tried forever to prove that they're also uniformly bounded for all n, but we failed. And in fact, the spectral gap is something between 1 over n to the 4 or 1 over n squared. So if you go away from 0 temperature, these Lindbladians don't have uniform spectral gap. If they don't have uniform spectral gap, if you go to infinity, you're screwed because CLSI implies spectral gap. So that doesn't work, right? You cannot pass to infinity. It's still nice that we can have some control at all, but yeah, but during the proof, we realized if we modify our resources a little bit and make them a little bit stronger, multiply by these operators, then it does work. So the choice of the resources are crucial, right? I mean, so if you, of course, the Pn of A and Pn of B, they really correspond to very simple models of photon emission and the kind of noise they produce, right? So they're super well studied. But this kind of photon emission I've not seen, but mathematically this is a good resource because it keeps this keeps these CLSI constants alive. Now, for these original one, we still have finite diameter, which is a little bit surprising. So this is an example where finite diameter at infinity and CLSI differ, right? So we can have finite diameter, but no CLSI. Just go to infinity, the finite diameter is uniformly bounded, limit it's also bounded, and there we go. Yeah. So here I come to the little bit of von Neumann algebras, which I want to consider. I will just try to convince you what kind of, in infinite dimensions, what should we try. So von Neumann algebras are not so scary, right? I mean, L infinity of omega mn is a type 1 von Neumann algebra, but infinite dimensional, and who doesn't like random matrices? They're so simple, aren't they? B of H is a trace. If you take an infinite tensor product of 2x2 matrices, like an infinite resource for computation, an infinite Turing band with non-commutative states, and you take the trace, you get the so-called hyperfinite 2-1 algebra, which has a nice trace and also has an analog of the maximally mixed vector. It's just the identity vector in the so-called GNS construction. GNS construction is an inner product given by that trace. If you modify that a little bit and use lambda over 1 plus lambda and 1 over 1 plus lambda as your reference state, you need a reference state to form the tensor product. That's just all I want to say, right? Without the reference state, the tensor product is not really well defined. So you need that. If you do that one, you get this would be a C-star algebra. If you go to the closure, you get a von Neumann algebra, and then you get the hyperfinite n lambda factor. Well, so they're not that scary. I mean, you can calculate everything in finite dimension, just pass to the limit and done. Yeah. Okay. Then, I will not talk a lot about the modular group, but I just tell you that for every state there is one. I think Nick did talk about the modular group, so I can skip this, right? So every state on the phenomenal hell has a modular group given by some, well, the problem is in type 3 or not tracial algebras, this D is not in the algebra, right? So if you are if you have a trace, the D is in the algebra. If you're not, you have to go outside. But here's the correction. This D is not the algebra. D to the IT x D to the minus IT is. And that theorem, I had a postdoc who explained that theorem, and it just took him a semester. You can do it in 2 weeks, but that's the theorem. Okay, that's the non-trivial part of Tomita Takazaki, or at least one, and it's characterized by this analyticity condition. So there's something nice to be said. This is the Hargrove reduction method. So when I started to do type 3 objects, I didn't like the definition, so I ignored it. And then I went to Unde, and I learned from Uwe Hargrove that there is a trick. If you have a normal facial state, you can go into a larger algebra. You can decompose this larger algebras in smaller pieces, and they all have a trace. And then you just have to condition back and get the limit. So this means even if you don't like modular theory, you can do all your calculations pretending you have a finite trace, and then use this method and say, I'm done. All calculations can be done in a tracial case, and you never have to worry about it as long as your properties are kind of compatible with conditional expectations. And this has one, right? So that's cheating. You know, I did modular theory calculations without learning modular theory, at least at the beginning. Later on, I had to. But anyway, so there is a way to get around that, and that's what I want to advertise here. And then there's classification. There are algebras with traces, type 1, type 2, 1, that have normal traces to infinity, and then there's the rest, you know, type 3. And this, unfortunately, are the interesting ones for some people. Okay, we have talked about this phenomenon algebra generated by this A lambda. So this is the modified tensor product with this particular state. Yeah. Now, then you can calculate the logarithm of the generator of the modular group. The logarithm of the sigma t has a generator on L2. You take the logarithm, you count the spectrum. If these things are of the form z times log L, so this is a discrete subgroup of the real line, which you obtain as a spectrum of an operator coming from your state. That's all you have to really remember, right? Every state, you can calculate a modular operator, or somebody can calculate a modular operator. You can calculate the spectrum of that. If the spectrum, if the ratios behave well, then you have a type 3 lambda factor. And then you can calculate the centralizer, and that's a 2-1 factor. If you take the tensor product of 2 of these guys, you get a type 3-1 factor, and with a very nice centralizer. So it's really a Lego system, right? You know, I understand n lambda and n lambda 2, and then I take the tensor product, I'm in type 3-1. These mysterious objects, which Hargrove proved are unique. Hyperfinite 3-1 factor is unique. There's only one guy. You know? But okay, so for all of these things, you will just see in a second that we can say something. What I should say is that this state construct from the tensor product state is not the state people want. And let me just skip. They don't want it because in algebraic quantum field theory, they want another state, you know, with a trivial centralizer. Okay, so we just answer that question for a given number of resources. How do we get comparing resources? Hyperfinite factor, we have billions of descriptions of the hyperfinite factor. So it's kind of, you know, for Neumann algebras, hyperfinite factor has many ways to appear as 2x2 matrices. I mean, it's kind of, you know, have many ways to get to the same limit object. That means you have many choices. You can, for instance, take one description using so-called rotation algebras. It's like a PQ, a discrete PQ relation. And then you find 2 generators, and then you 2 resources do exactly. They have CLSI, finite diameter. With 1, it doesn't work, but you need exactly 2 as the minimal number of resources. So hyperfinite factor, you can choose it to be 2. You can choose it to be 3 if you want to use our action before, but that's it. 3 lambda factor because of the periodicity of the modular group, you can get away with 3. You essentially, you project down onto the states which are operators which are invariant in the modular group. That's a hyperfinite 2-1 factor. Then you need the other one from before. So you get away with 3 for type 3 lambda 3.
What are the generators here? 3?
Huh?
What are the 3 losses that you're using here?
And so here, I'm taking in this I'm using sort of the logarithm of the generators of the car algebra, right? Some version of logarithm. I mean, you have to write this down more carefully, but a suitable choice of logarithm does the job. And then if you do this for the hyperfinite factor, if you have the type 3 factor, you go from the whole algebra to the centralizer by averaging over the modular group. And then you need another 2. That makes 3. Yeah, I mean, it's really that kind of very simplistic picture which gives you the right answer. And yeah, I have no idea what to do in type 3-1. If I want to fix the quantum field state, because it's not the tensor product state, it's another state. And that state has trivial centralizer. And then I don't know what to do. So that's the open problem, right? One of the open problems.
But you didn't say that. I mean, you showed that you can get by with 3, but you didn't show that you cannot with 2.
I did not show that you cannot do with 2.
Oh, yeah.
I just, yeah, for a hyperfinite factor, I know I cannot get away with 1.
But beyond the hyperfiniteness, it's an open game.
Absolutely. I mean, it's also the question, even if I can find, some set, but in a given problem, what the resources are. So it's, I mean, this is kind of a little bit of a backwards game, right? Because in a given situation, you would know, this is the resource I care about. And then you have to ask what happens to those. But if you really want to have something, okay, what is the smallest number? Then that's how. And I only know for type 3 lambda, I get away with 3, which have finite diameter and CLSI. So it also, what extra properties do I want anyway? Yeah, and that is the black hole, which I'm willing to explain to anybody. No, I cannot. I mean, I can explain you what happens, but that's for another day. But it's the only thing I want to say is for these black hole pictures, if you do the right interpretation, they start with. So this is a picture. Oh, that was a little bit too energetic. So they often start with such a picture, which I had a hard time understanding. And what really happens is here, there should be a type 3-1 von Neumann algebra sitting. All these lines have type 3-1 von Neumann algebra sitting there, right? And they're here. Here and here, what happens here and there, I don't know. But my student explained to me that I should think of this being the past and this being the future. Put a black hole in the middle. And then these are the geodesics. You travel into geodesics. That is the modular group. And if you want to go into the black hole, you have to travel from here to here. And he can show that if you travel from there to there, that is not accessible from the left and right algebra. So he has a way to prove that if you fall into the black hole, you lose some information. By constructing type 3-1 algebras, which reflect certain symmetries. He constructs type 3-1 algebras and certain symmetries are preserved. And then one can do some calculation by the construction. So that's kind of, but don't ask me what are the best resources here because I don't know. Yeah, so that's just outlook, okay? You can, if you're creative, maybe one can say something in the distant future about black holes, and I'm done. Thank you.